Welcome everyone. We're gonna continue previous session on space virtualization, LXC, LXD, and Docker. In modern computing, virtualization and containerization have become fundamental technologies for building scalable, secure, and efficient infrastructure. They allow multiple isolated environments to run on the same physical hardware, but they achieve this in fundamentally different ways. This topic begins by exploring hypervisor-based virtualization, starting with Type 1 hypervisors, which run directly on hardware and provide a strong isolation and performance for running full virtual machines. We will also look at the concept of hardware virtualization, where CPU features such as Intel VTX and AMD-V enable efficient execution of guest operating systems. From there, we transition into the world of containers, focusing on how they differ from virtual machines. We will compare LXC Linux containers, Docker engine, and traditional VMs, highlighting differences in architecture, performance, isolating, and use cases. A structured comparison table will help clarify when to use each technology in real-world scenarios. Finally, the topic becomes hands-on with LXC practical labs, including installation on both Debian and Rocky Linux systems. You will learn about privileged versus unprivileged containers, how container permission affects security, and how to properly configure networking for LXC containers. This includes creating a working network bridge, launching and managing containers, and setting up a simple and reliable container network environment. To reinforce learning, we will also cover essential LXC commands and provide exercises that help solidify understanding through practice. By the end of this module, you will have a clear understanding of a virtualization versus containerization and practical experience working with LXC in a real system environment. Before containers became popular, companies needed a way to run multiple operating systems on a single physical server. Imagine we have one powerful server, but we need Windows for Active Directory, Linux for a web application, and another Linux server for a database. Buying 3 physical servers would be expensive and waste resources. This is where hardware virtualization comes in. The software that makes this possible is called a hypervisor. A hypervisor sits between the hardware and the virtual machines. Its job is to divide the hardware resources such as CPU, memory, storage, and networking among multiple virtual machines. The important thing to understand is that hypervisors virtualize hardware, not the operating system. Every virtual machine believes it has its own computer, even though it is sharing the same physical hardware with other virtual machines. Some common examples include VMware ESXi, Proxmox, and Linux KVM, which are commonly used in data centers, and VirtualBox or VMware Workstation, which are often used on laptops for testing and learning. Hypervisors enable hardware virtualization by using CPU virtualization extensions such as Intel VTX and AMD-V. These technologies allow guest operating systems to execute efficiently and securely on virtual machines with hardware support rather than relying solely on software emulation. Intel VTX and AMD-V are hardware virtualization technologies built into Intel and AMD processors. Their role is to provide CPU support for virtualization, allowing hypervisors such as KVM, VMware ESXi, VMware Workstation, VirtualBox, and Hyper-V to run virtual machines more efficiently and with lower overhead. Types of hypervisors. Hypervisors are divided into 2 categories, Type 1 and Type 2. Let's start with Type 1 hypervisors. Type 1 hypervisors run directly on the physical hardware. There is no Windows or Linux host operating system sitting underneath them because they communicate directly with the hardware. They provide better performance, better security, and lower overhead. This is why cloud providers such as AWS, Azure, and Google Cloud use Type 1 hypervisors. Examples include VMware ESXi, Proxmox, Linux KVM, and Microsoft Hyper-V. Now let's look at Type 2 hypervisors. A Type 2 hypervisor runs on top of an existing operating system. For example, your laptop might be running Windows. You install VirtualBox on Windows and then create Linux virtual machines inside VirtualBox. In this case, requests must pass through Windows before reaching the hardware. Because of this extra layer, Type 2 hypervisors are slightly slower than Type 1 hypervisors. However, they are much easier to install and are excellent for learning, testing, and development environments. A simple way to remember this is Type 1 equals production and cloud environments, Type 2 equals desktops, laptop, and learning environments. How hypervisors work vs containers. This is the most important slide of today's lesson because it explains the difference between virtual machines and containers. A hypervisor creates virtual hardware. For every virtual machine, it creates a virtual CPU, virtual memory, virtual storage, and a virtual network card. The virtual machine thinks this hardware is real. Each virtual machine then installs its own operating system and its own kernel. This means a Windows VM can run next to a Linux VM on the same physical server. Because every VM contains a full operating system, virtual machines require more CPU, memory, and storage. Now compare that to containers. Containers don't virtualize hardware. Instead, containers share the host operating system kernel. Because they share the kernel, containers start much faster and use fewer resources. An easy analogy is this. Containers are like apartments in the same building. Everyone shares the building structure, plumbing, and the electrical system. Virtual machines are like separate houses. Every house has its own plumbing, electrical system, and structure. As a result, virtual machines provide a stronger isolation but consume more resources. Containers are lightweight and efficient, while virtual machines are heavier but offer complete operating system isolation. If you remember only one thing from this lesson, remember this. Containers share a kernel. Virtual machines have their own kernel. That single difference explains most of the advantages and disadvantages of each technology. Comparison table: Linux container versus Docker versus virtual machine. First release for LXC is 2008, for Docker 2013, and for virtual machine 2000. LXC is invented by Linux community, Docker is invented by Solomon Hykes, and virtual machines by multiple vendors, IBM, VMware, Xen, and Microsoft. LXC focuses on system containers, Docker on application containers, and virtual machines hardware virtualization. LXC used shared kernel, Docker shared kernel, and virtual machines separate guest hours. Boot time in LXC is seconds, in Docker is also seconds, and for virtual machines, minutes. LXC has init systems, Docker no, single process, and virtual machines yes. LXC is ideal for system containers, cloud infrastructure, Docker for application and microservices, and virtual machines for enterprise virtualization. Here is the cheat sheet for your next exam or interview. If you need to run a full light Linux environment that acts like a server, use LXC, for example, DNS server, DHCP server, and so on. If you are building a microservice that just runs a single web server, use Docker. If you need to run a completely different OS, like running Windows on a Linux server, you must use a virtual machine, because containers require a shared Linux kernel. Modern infrastructure often combines all of them. Hypervisors for infrastructure layer, LXC container light virtual machines, Docker containers, application layer. Hands-on lab, install and running LXC. I'm gonna to show you how to install LXC on Debian based systems. Before we start, ensure you're on a modern Linux kernel. We are aiming for unprivileged containers today. This is the best practice for security. It ensures that if a container is compromised, the attacker doesn't gain root access to your host machine. First, I'm gonna open VMware Workstation and start the Debian virtual machine. Then I'll enter the password to log in. After that, I'll open the terminal. And adjust the font size by pressing Ctrl++ to increase the text size. First, update and upgrade. We'll install the core Linux package along with a few power tools. Notice we are including libpam CGFS. This is essential for those unprivileged containers I mentioned, and bridge utils for advanced networking. Go ahead and run this command. apt install LXC, LXC templates, UID map, the bootstrap, bridge utils, aparmore utils, libvirt0, libpam CGFS. Hit the enter. UID map, required for unprivileged containers, essential for security, maps container root to a non-privileged user on the host. libpam CGFS handles C group delegation, allows non-root users to manage their own container's resource limit, CPU and RAM, for example. Bridge utils, network bridging, crucial for bridge networking, allowing containers to act like real devices on your local network. The bootstrap build tools for Debian allows you to pull and create fresh root file systems for Debian-based distros. AppArmor user space parser utility for AppArmor. AppArmor utilities for controlling AppArmor. In our screen we see continue, yes. This is the package manager calculating dependencies. Installing packages is a standard because we are setting up a full virtualization stack, not just a single binary. If you are using different distros, remind that Ubuntu is usually plug and play for LXC, but Debian requires this specific package to ensure the kernel features like C groups are properly configured, and also more configuration is needed. Installation isn't enough. We need to verify that our Linux kernel is ready to act as a hypervisor. We do this by running LXC checkconfig. Think of this as a pre-flight checklist. If any of these items show as disabled or missing, our container simply won't start. What are we looking for? Especially namespaces and C groups. Namespaces are what give each container its own view of the system, like its own host name, process list, and network. C group control groups allow the host to limit how much CPU or RAM a container can steal from the rest of your system. Kernel config. If LXC checkconfig says kernel configuration not found, don't panic. It just means it's looking in a default location. The output shows it automatically found the right one in /boot/config. Namespaces. If user's namespace is disabled, you cannot run unprivileged containers. This is the most common reason for permissions denied error later on. C group v2. You will see both v1 and v2 listed. Modern Linux like Debian 13 Trixie uses C group v2. It's the new standard for managing system resources. and what is not loaded. You might see vEthernet pair enabled not loaded. This is normal. The kernel is capable of using these features, but it won't load them into memory until you actually start your first container. It's a smart resource saving design. As you can see here, all of the important settings are enabled. We're green for takeoff. In the world of DevOps, security is a first-class citizen. We have two ways to run containers, privileged and unprivileged. If you run a privileged container, the root user inside the container is the actual root user on your host. If a malicious script breaks out of that container, they have total control over your machine. We always prefer unprivileged containers, where the container's root is mapped to a regular low privilege user on the host. Think of it like a cage. Even if the animal gets out of the cage, it's still locked in the room. We need to tell the kernel that our user is allowed to own a range of IDs. We check /etc subuid and subgid. These numbers, like 100,000, are the starting point for our container's internal IDs. We also enable user namespaces. This is a specific Linux kernel feature that allows us to pretend we are root inside the container while remaining a normal user to the host system. When you get a permission error in LXC, 90% of the time it's because the ID mapping in subuid or default.conf are mismatched. On Debian-based systems like Ubuntu and Mint machines, you must explicitly enable this kernel unprivileged username clone feature in the kernel using sysctl. If it is set to 0, the kernel will block any non-root user from creating a container. We use the T command here to write to the system configuration permanently so it survives a reboot. The dpkg reconfigure command. This command refreshes the package's internal state. It is reset bottom for the LXC service settings. In the next step, we create a configuration file for our user. This ensures that every container you create from now on inherits these secure settings automatically. The LXC.id map lines are the magic here. They map the container's root to that safe range we defined earlier. We touched on AppArmor earlier. Think of it as a security guard for your processes. Sometimes it's too strict for the environment we are building, causing permission denied errors. By setting LXC AppArmor profile unconfined, we tell the system to use a slightly more flexible profile for our container, which prevent these common configuration crashes while still maintaining the core isolation provided by user namespaces. Consider that .config LXC default.conf is for the current user. If you create a new user on the system later, they will need to repeat this configuration for that user as well. Containers need to talk to the internet, but they are isolated. We use a bridge. Imagine LXC bridge as a virtual switch inside your computer. All your containers plug into this switch, and the switch connects to your host's network card using NAT, acting like a router. VNet stands for Virtual Ethernet Pair. It's like a virtual patch cable. One end goes in the container, the other plugs into the bridge. We are using NAT, Network Address Translation. The containers are hidden behind the host's IP. This is exactly how your home router hides all your devices behind one public IP address from your ISP. The LXC Net service is our automatic setup wizard for this. Debian usually provides automatic networking via LXC Net. We're gonna to check sudo systemctl status LXC net. It's okay. We're gonna verifying network. IP address show LXC BR0. Good. If LXC0 doesn't show up in IP address, the bridge wasn't created. Stop and debug the service first. As you can see here, all important settings are correct. This is the most common pitfall. Even if you have the bridge set up, the system won't let you unprivileged user plug into it unless you give them permission. This file /etc/lxc/lxc-usernet is that permission slip. I'm gonna open this file and add this configuration. You're telling the system my user sysadmin is allowed to create up to 10 virtual network interfaces on the bridge LXC BR0. The current logged in user is checked using the whoami command, which confirms the active user as sysadmin. The configuration shows that the user sysadmin is allowed to use the VNet interface on the LXC BR0 bridge with a limit of 10 connections. Adjust it with your desired user. Without this, your container will fail to start because they can't get a network card. We've done the heavy lifting of security and networking. Now we use LXC create tool. Think of this like a package manager for operating systems. By using the download template, we pull down a pre-built hundreds file system from image.linuxcontainers.org. We aren't installing from an ISO file like a VM. We are simply unpacking a root directory that is ready to run in seconds. You can do this interactively where it asks you for the distro and release, or you can script it using flags like dist and release. LXC create-t download pulls the OS image. This is infrastructure as code. You're defining a machine with a single command. We're gonna run LXC create-n my container-t download. Distribution could be Fedora, Ubuntu, or whatever you like. Release or version. And architecture. Usually AMD 64. That's it. In DevOps, we almost always prefer the non-interactive method because it makes our infrastructure reproducible. You can turn that command into a script to launch 100 containers exactly the same way every time. Now I'm gonna run the next method, LXC create-n Debian elf -t download -dist Debian -release bookworm -arc AMD-64. LXC ls-fancy shows container status. Essential for monitoring, it tells you which containers are running and their network status and etc. Unprivileged containers stored in home require directory traversal access. If you see cannot access /home/sysadmin permission denied, here is a classic issue. When you run an unprivileged container, the container's root user tries to reach into your home directory to store files. But since your home directory is private, the system blocks it. We used setfacl set file access control list to give the container's virtual user just enough permission to enter the folder. We aren't giving it full access. We are just granting execute or traversal rights so it can find its own files. I'm gonna fix it. Now check pad. Name I-L, debuggs pad permissions, a diagnostic superpower. It shows you exactly where along a pad a permission is denied. Every container has a brain, its configuration file. In home/local/share/lxc/container name/config. This is where you define its limits. Want to restrict a container to only use 512 megabytes of RAM or one CPU core? You edit this file. It's also where you lock in the network settings we defined, ensuring that every time the container boots, it connects to our bridge LXC bridge 0. After making changes to this configuration file, you must stop and start the container for the new settings to take effect. LXC stop-n container name, LXC start-n container name. Next step is container network configuration. The lines I provided define a virtual Ethernet network interface for my container. Here is what each line does. LXC.net.0.type equals v Ethernet. This sets the interface type to a virtual Ethernet pair. One end of the cable stays in the container and the other end is connected to the host. LXC.net.0.link equals LXC bridge 0. This tells the container to connect to a virtual bridge named LXC bridge 0 on your host machine. This bridge acts like a virtual switch, allowing the container to access your host's network and usually the internet via NAT network address translation. LXC.net.0.flags equals up. This command ensures that the network interface is initialized and set to the up active state as soon as the container starts. LXC.net.0.name equals Ethernet 0. This defines the name of the network interface inside the container. Regardless of what the host sees, the OS inside the container will perceive its network card as Ethernet 0. I'm gonna repeat that for Debian LXC. Okay. Last step is starting and attaching to containers. Here is a distinction that trips up many beginners. Starting is like turning on the power button of a PC. It turns the boot process in the background. Attaching is like sitting down in front of the monitor and keyboard. LXC start-n my container powers it up. List running containers, LXC ls-fancy. Okay. And LXC attach-n my container drops you right into the root shell of that container. If your container fails to start, don't guess. Use the debug flag LXC start-n name -l debug -o LXC log will tell you exactly which line or permission is failing. List running containers, LXC ls-fancy. When you see that bytes from 4.2.2.4 output, you know your sandbox is officially connected to the outside world. The ultimate test of a successful container setup is networking. If you can reach the internet from inside the container, your NAT, bridge, and ID mapping are all configured perfectly. For more information, visit my website at itstorage.net, click on SAN Storage Virtualization, and then go to Linux LXC Virtualization. I have provided how to install LXC on Red Hat based system as well as more advanced configurations like LXC DHCP reservation and auto start configuration, etc. Exercise. This exercise demonstrates real-world usage, deploying service inside containers. Task: create Ubuntu LXC container, start it, install Nginx inside. Expected output: running container and Nginx is installed. Now pause the video and try to do this scenario. I'm gonna show you step by step. First, create the container, LXC create -n my Ubuntu container. I also give distribution release and architecture. I'm gonna use default bridge for network configuration. Second step, start the container in the background, LXC start -n my Ubuntu container -d, and then update the package index inside the container, LXC attach -n my Ubuntu container --apt update. Next step, install Nginx, LXC attach -n my Ubuntu container -apt install -y Nginx. Next step, check container status, LXC info -n my Ubuntu container. And the last step, check Nginx status inside the container, LXC attach -n my Ubuntu container systemctl status Nginx. As you can see, all steps were executed correctly, and our system now looks like running container Nginx installed. Useful LXC commands. These are essential commands students should memorize. Whether you're creating, starting, or destroying containers, this table will be your best friend during your day-to-day work. You've now mastered the foundation of containerization by building LXC environments from scratch. You've moved beyond simple commands to understand the kernel-level engineering that powers modern DevOps. You learned the key ideas, namespaces. We have seen how the kernel creates independent views of the system, keeping processes, networks, and file systems separate. C groups. We have used the kernel to act as a regulator, strictly limiting CPU and memory usage to ensure system stability. The reality: a container isn't a separate machine. It's a managed, restricted process running natively on your host kernel. Now you understand what tools like Docker and Kubernetes are built on. So they're no longer black boxes. You can think more clearly about how systems work, troubleshoot issues, and design better infrastructure. Congratulations! You have gone from installing the LXC package to deploying, securing, and networking a fleet of containers. You now have the skill to build custom labs, run isolated environments, and master the fundamentals of Linux containerization. Remember, practice makes perfect. Don't be afraid to LXC destroy a container and build it again. That's exactly how you get comfortable with the process. Feel free to leave your questions in the comments. I'll get back to you. That's enough for now. Great work today. Take a break and we will continue building your skills in the next session. See you then.